0. And then I'm done. So it's taking limit as well goes to infinity, we get the absolute value of the second derivative, right, is actually 0. And then f of and that is for all a, right? Because I didn't have any restriction about a, right? A was for all a and z, and that means that f of z is actually a plus b. So the second derivative vanishes, so the first derivative has to be constant, then f has to be an antiderivative. Questions about this? So I was given an inequality, right, on the modulus of the function, and I wanted to conclude something about the derivatives. So I used Cauchy integral formula and then bound the value of the derivative, right, by bounding the value of the integral. And now because the radius where the function is an elliptic is arbitrary, right, you can take that limit as goes to infinity and you get this one. There is a similar problem, which I won't do here, but then recommended. That is exercise, exactly the same idea. Exercise 5.8 says, suppose that f is entire. The following inequality holds, right? And the absolute value of the derivative of f of z is less or equal than the absolute value of z for all z. Then, well, f of z is actually of the form a plus b c squared, with absolute value of b less or equal than 1/2. Now this if you're going to try to solve this problem, right, and you just use the idea that the way that I solved the other one, right? So what would you try to do? You have to prove, right, that f of z is a polynomial of degree 2. So you would like to prove first that what? That the third derivative vanishes. Is that right? Now how do you use the third derivative? Well, you write the Cauchy integral formula for the third derivative, right? Now, in which way can you write the Cauchy integral formula for the third derivative? You don't want to write it in terms of f, right? Because the condition that you are given here is not in terms of f, it's in terms of f prime. Is that right? But what you can do, so here maybe the hint, right? Is to consider instead, right, g of z to be the derivative, right? So if I want to prove that the third derivative of f vanishes, right, it's the same as proving that the second derivative of g vanishes. Is that right? We want to prove that the second derivative of g is 0, and the second derivative of g is 0, that means that the third derivative of f is 0, and that will give you that f is a polynomial degree 2. All right? Now, those conditions, they just come from considerations of the inequality. But the good point about considering G is that the inequality becomes an inequality on G, right? Because the inequality becomes what? The absolute value of G of Z is less or equal than Z for all Z in the complex numbers, right? Now you are very similar setting, right? You have to prove that the second derivative of function is 0, right? And you are agreeing that the absolute value of the function is less or equal than the absolute value of Z, right? So it's very similar to the other one. Actually, is it the same? Right? It's exactly the same, right? Because the constants here are A and 1. Okay. So you finish it up. It's very similar to it. Now I just made that problem into the one before. So. Questions? Cool. Maybe let me. So you should finish this one. Sure. Even more than that, it's just more general. So let me write here this. There's some extra. We are in extra what? Like extra 10 now? Is that extra 10? Whatever. I think it's extra 10. Extra 1 something. I think it's extra 10. I don't know. So it's if, right? F is entire. And the absolute value of F, right, is bounded by the absolute value of a polynomial. See it in complex numbers and some polynomial of degree capital N. Right? So what do you think you can prove? So the condition before, right, was that the absolute value of the function, right, was less or equal than, this is the absolute value of a polynomial of degree 1, right? And then we proved that the second derivative vanishes. Right? If this was a polynomial of degree 3, maybe I could prove that the fourth derivative vanishes. Right? And then I would say that G is a polynomial of the same degree, right? So here, right, I will prove that G is a linear polynomial, right? Because it's bounded by the absolute value of some linear polynomial. So if the absolute value of F is less or equal to the absolute value of a polynomial of degree n, then F has to be itself a polynomial of degree n. So you should complete the details for this one. This is very simple. But that one is not in the booklet. I guess that's the right thing. Questions? Yes.
If polynomial degree n is that actually fraction?
What?
Actually fractions, like your highest order would be a fraction degree?
No, in this case, it's not. It's not. It's a polynomial is positive integers. The degrees of positive integers. All the parts of positive integers. Of course, this is more general, right? Because we saw in the example before was with a fraction, right? In this case, it's actually that is no power here, but the power could be a little bit more than 1, right? For that thing to work. But if you just want to buy a polynomial, you can get a conclusion. I mean, you can go a little stronger than this, but this is good. All right, so now for the theorem. This is Morera's theorem. And it's actually we basically already proved this. This was kind of cool. Says the following: if f is continuous, on a region D, right? Now this is not analytics, continuous function. Continuous function of region D. And it happens that when you take the integral for every closed rectangle, R in D, right? So the boundary of the rectangle has to be also in D. With boundary gamma, so you have a function that is continuous in a region D. For every closed rectangle with boundary gamma, it happens that when you take the integral along gamma, you get 0. The integral over gamma of the function is 0. If that happens for every closed rectangle that you have inside the region, then f is a nullity. This is a converse, right? We already proved the opposite for this. We proved that the function, right, is this is like the opposite to the rectangle theorem, right? The converse to the rectangle theorem, because the rectangle theorem says, well, if your function is analytic in a region, and if you have any closed rectangle, then you integrate along the boundary and you get 0. Right? Now this is the converse, which is much stronger, right? It says that is enough to say that the function is analytic. Actually, everything is rectangle theorem, basically. So if the hypothesis of the rectangle theorem is satisfied, if and only if the function is analytic. The proof, extremely easy. Extremely easy. So first, now take a small disk. The center C0 and some radius, right? And well, for every point in the region, you can find a small disk, right? Because the region is open by definition. So for every point in the region, you can find a small disk that is inside. So take a small disk inside. So center at C0, radius R. Then define the function capital F of z as the integral from z0 to z of the function f. So that will be that. Exactly the same as the proof of the integral theorem. That's how we define the antiderivative. Right? Now, what do we mean by the integral from z0 to z? Exactly as before. We are now on a disk, right? It has center at z0. You take any other z, right, there, and then you can move horizontally first, and then vertically until you reach. Right? And this is the integral from z0 to z. It's moving horizontal and then vertical. Exactly the same as in the proofs of the integral theorem. Of course, that is only possible if z belongs to the disk, right, with center z0. Okay. Now, the proof of the integral theorem, right, proves, uses the rectangle theorem, right, to get a very nice relation for f of z, right, if you remember. So, as in the proof, of the integral theorem, the fact that the integral over the boundary of every rectangle is 0. Implies that if you take, right, the integral from z0 to z plus h, right, of f of w dw, that is the same as the integral from z0 to z f of w dw plus the integral from z to z plus h. It's exactly the same. You just draw the picture and then you see there is this rectangle, right, where the integral is 0. And then you get this isolation and you can break the integral, just as you do it in calculus. Right? So the cycle is an idea. And then, let's say that if you take f of z plus h minus f of z over h, right? That is really 1 over h integral between z and z plus h of f of w dw. And so what happens if you take, right, the absolute value of f of z plus h minus f of z over h minus little f of z. So if I say, okay, what is what I want to prove here? I want to prove, right, as in the integral theorem, right, that is an antiderivative for f. So if that is an antiderivative for f, I want to prove that that function is actually differentiable, right, and the derivative is f of z. That means I want to prove that this modulus, right, goes to 0 as h goes to 0. Right? Because that would imply that the limit as h goes to 0, this part is exactly this. That means that capital F is an antiderivative of little f. Right? But then what is that, right? That part here is just this, right? So that's the 1 over h, right? Integral from c to c plus h to f of w dw, right? Minus f of t. And what is that? Well, what I can do is multiply by take f of z, multiply by h, divide by h, that's equal to single h, right? So that is equal to the integral between z and z plus h and modulus, our modulus of h, right? Of f of W minus f of z dw. And that is because the integral between z and z plus h of f of z dw, what is that? Well, if that integral, right, with respect to w, the f of z is constant, so you can take it out. And you get the integral between z and z plus h of dw. Right? But then by the fundamental theorem of calculus, right, this is just h. Because an antiderivative for dw is w. Right? For one is w, and you evaluate as c plus h minus z. So you get c plus h minus z, which is h. So that gives you exactly the same as h times f of z. Right? So if I multiply by h, f, and divide by h, this part that gets multiplied by h can be written as that integral, and I can put everything inside the integral. I have already done this proof, because that's how we prove the integral theorem, right? So it seems like all the same. But I just want to make a remark here that what we really use was that the function f was continuous. Is that right? Because now you want to bound this, right? And to bound this, you put the absolute value inside, and to bound the absolute value inside, right? You really use the function is continuous. That's all what you use, right? So that is necessary that the integral between z and z plus a, right, of the absolute value of fw minus f of z dw all over absolute value. But now you know that f is continuous, right? So for given epsilon larger than 0, it exists a delta larger than 0 such that absolute value of z minus w less than delta implies absolute value of f of w minus f of z is less than epsilon. That is because f is continuous. So that is the definition of continuity. And now we have to check if is it possible, right, that the z minus w is actually the distance between z and w is actually less than delta, right? And then you wonder what is the w really? W is on the path that joins z and z plus h. Right? So you just have to do a loop diagram here to realize what's going on. So you have, right, your z here, or your a was in the middle, your outputs here. So you have z here, and then you have z plus h here, right? So the h was really that vector, right? And the path that you were choosing, I don't know it. So this is h, this is z, this is going to be c plus h, right? And then the path that you are choosing to integrate on, right, is this one, right? So the w's are all here, right? That's what the w's are, right? And then what is the difference between z and w? The modulus, right? The distance between z and w, right? Cannot be more than h, right? If it's here, right, it's at most that distance, right? Which is smaller than h. And if it's here, right, each of those ones, right, have distance more than h. So the distance of this guy is less or equal than the magnitude of h. So, right, the distance between c and w is equal to the magnitude of h for all w on the path of integration. Oh, but I'm taking the limit as h goes to 0, right? So I can make the modulus as small as I want, right? So taking h so that the modulus of h is less than delta, right? We get, right? We get that absolute value of f of w minus f of z, right? Is less than epsilon. Is that right? Because if the distance between z and w, I know that that is less or equal than the absolute value of h, right? But if the absolute value of h is less than delta, then I know that the distance between z and w is less than delta, and that implies that the distance between f of w and f of z is less than epsilon. So as long as I choose h that has magnitude less than delta, I will have this. But that says what? That says, oh look, if you take that, then the absolute value, right, of the fz minus fz plus h minus f of z over h, right, minus f of z, right, is really less or equal than what? Less or equal than this guy, right? But that is less or equal. This guy here is less than epsilon, right? So that is actually less than epsilon over the magnitude of h, right, times the integral between z and c plus h. Did that? But this measures the length of the integration path, right? And what is the length of the integration path? Well, this side is at most h, and that side is at most h, right? So the length of the integration path is at most 2 times the magnitude of h. So this is, right, oh, well, then we are done, right? So we prove, right, that as h goes very small, right, because as long as h is less than delta, right, this magnitude is less than 2 epsilon, which is your new epsilon, right? So we prove that the limit of this guy is this guy. That means that f is an antiderivative for little f. Oh, that means that capital F is analytic. But if capital F is analytic, it's infinitely differentiable. So has first derivative, has second derivative, has all derivatives. So what is the second derivative of capital F? Oh, they gotta be the first derivative of F, right? Or the derivative of little f. So little f has to be analytic. So that's the trick. So instead of proving directly that little f has a derivative, you prove that little f has an antiderivative, and then because it's infinitely differentiable, just carries on little f. That is the trick. Then capital F is analytic, and the derivative of f is little f, right? Of course, for as long as it is in the little this, right? But center is 0 and radius r, right? That was inside the region, but it's for every z0, so it doesn't matter. So, and then f is analytic, right, and the derivative is equal to z, but this also implies that f is infinitely differentiable. So the second derivative, for instance, is f. Right? Okay, I'll stop there. That's more or less there. So rectangle theorem and analyticity are basically the same thing, and they are the same thing as having power series expansion. Right? Because if the function is analytic, has a power series expansion, but if you have a power series that converts to a function, that power series has a derivative, right? So having derivative and having power series expansion, they're the same thing. But that is also the same as having rectangle theorem, right? If the function is continuous and has rectangle theorem, then it's analytic, so they're always so, anyway, I'll show you a couple more applications tomorrow. But then today is the last thing that is included for the